Here's a brief overview of the agenda. First, I'm going to take you through a tour of a few of the new features in BigML, and then we'll spend a little more time looking at our new Anomaly Detection service. And then I'll give you a preview of a few features that will be released very soon, and then, as Andrew mentioned, we'll open for questions at the end. All right, so the first new feature that we're going to look at is called model clusters. So the idea here is to use models to discover rules that describe the clusters generated by a clustering algorithm. Here's how it works. We start with our unlabeled data set, and from this we create a BigML cluster. Then if we want to understand how a specific cluster, say cluster number 5, differs from the rest of the clusters, we build a new data set by adding a feature to the original data set. This feature has the value of true if the instance is in cluster 5 and false otherwise. Now we can model this new data set, and since the decision tree is essentially an if-then-else rule set, we'll now have a compact expression that describes how this cluster differs. Now let's do an example. In our last webinar, we introduced our then new clustering service. One of the use cases we examined was analyzing a data set of whiskeys to group them together by their flavor profiles. We're going to quickly repeat that demo, but this time we're going to extend the goal. Rather than just group them, we want to discover the rules that distinguish the clusters from each other. That is, we want to see an expression of how the flavor profiles differ. So let me log in. And I have this source is in S3, so I'm going to go ahead and pull it in from an S3 URL. And just to refresh the contents of this data set, we can see that we have, at the top, we have a label which is just telling us the distillery that each whiskey came from. And then we have these measurements on a scale of 0 to 5, body, sweetness, smoky, medicinal, etc. And I don't want that to be text, so let me just fix that real quick. And we'll go ahead and create our one-click data set. And then we'll do, whoop, not a model. Configure the cluster. We'll do that. So here's something that has changed. If you go back to the old webinar, what we did to have the clustering algorithm ignore the distillery feature was we actually scaled it with a value of 0 so that it would still be in the resulting cluster but wouldn't be considered in the actual clustering algorithm. We have this new feature here called summary fields where we can actually put in a field for exactly that express purpose. So we'll add that in there. And the other new option here is the model cluster. So by default, we don't model clusters, but if we just check that, then as we build this cluster, we'll be able to build the models from it automatically. Let's go ahead and let that run. So in case you missed it, that one little button I clicked before create cluster enables the new feature that I was describing. All right, so here we have, as before, our view of the cluster. We have these different groups of whiskeys, which should have a similar flavor profile. And we have this one rather strange cluster that's hanging out here, so let's go ahead and have a look at that one. And if I lock the display with Shift, then when I scroll down, I'll see I have two options here. So this was here before. This gives us the ability to create a data set with just the instances from that selected cluster, cluster number 6. And next to it, now we have this feature where we can create a model. So let's go ahead and let that run. And now we can actually, well, we can just hover around and take a look. But here we can get an idea of what describes the whiskeys that are in this particular cluster. And we can see that they either have a high value for the medicinal flavor, or they have if they don't have a high value, then they have a high smoky. Oops, that was true. Yep. Or if they're missing, if they're low on both of those, then they're not in cluster 6. So that gives us a really nice, compact way to describe the features of the whiskeys that are in this. So I could now, maybe I could go back and label this as, medicinal or smoky whiskeys are all in this group. And we could actually even see this as rules exactly. right. The next new feature we're going to look at is called missing splits. Now, one thing we know to be true is that real-world data is messy. And so BigML provides a lot of ways to deal with missing data. Here's just a quick summary. First, in the source view, you can define the tokens that represent missing values. There are several predefined tokens, but you can extend them easily. Next, you can use our dataset filtering to remove instances that have missing values. Or if you'd rather keep those instances but fix the missing values, you can use the Add a New Feature tool to replace missing values. For example, if you have an age in your dataset, you could replace the missing ages with the mean of the population, or 0, or whatever makes sense for your analysis. In fact, since the clustering algorithm is sensitive to missing integer values, we provide an option to automatically replace missing numeric values with the default that you specify. Now, at prediction time, missing values can also be a problem. I mean, if the tree encounters a split on a feature for which the input data doesn't provide, then how can the prediction proceed? To handle this, we offer proportional predictions. Basically, it descends both branches and then combines the results in a statistically significant way. But sometimes there's signal to be found in the missing data. Imagine if you were analyzing a data set of network packets. A missing TCP flag may be very important. So to handle these situations, BigML now offers the ability to make splits in the model based on missing values as well. So I'm going to give you a quick demonstration of that as well. And it's worth mentioning or showing again in the create or configure cluster, there's this default numeric value. So this is another example of the clustering algorithm is sensitive to those missing values, and so you can actually replace them automatically. Well, let's see the missing splits. All right, so this data set is it's actually a slightly modified version of the German credit data set, probably in the UCI repository. But basically we have these properties of individuals that are looking for a loan, and then there's a label down here called class, which is supposed to represent whether or not that individual is a good or a bad loan risk. And we see one of the variables that is provided is this checking status, and we can see that there's no checking, but there's also nulls. So what's the difference between no checking and null? Well, no checking means that, imagine you're filling out an application, you put down, I don't have a checking account, versus you don't put anything at all. You don't admit to not having one, or you don't have one, you don't get a bounce. So no checking account is different than there's no answer for that question. And so we're going to see if we get a different behavior using the missing splits on null for that. So let's go ahead and do the one-click data set. And from this, we can actually just do a one-click model and have a look at the tree real quick. All right, and we'll find for the first split in our tree is it is making its decision based on the checking status. And to the right, we have the customer doesn't have a checking account. And over to the left, we have, or sorry, doesn't not have a checking account, sorry. And to the left, we have that the checking status is no checking. So these are the people that do not have a checking account. All right, but because those instances that have checking status null, there's no splits on that value. So let's go back and fix this so that we can make our decisions based on missing values as well. All right, so rather than one click, we'll go into the Configure Model panel, and we'll open this Configure subpanel, and you'll see the options right here for missing splits. By default, it's disabled, so let's go ahead and enable it. All right, and we get a very similar tree. We're still splitting on the checking status first, but to the right side, we see now that the right branch is the checking status is not that they have no checking account, or that it's missing. And we immediately see this extra little node here, which is that additionally, if the checking status is missing, then it's already predicting that this is a bad loan risk with a confidence of 83%. So this entire little branch didn't exist before because we weren't splitting on that missing value. All right, so another new feature is the availability of online predictions in the UI. So previously, when using the prediction tool in the UI, each prediction request is sent to BigML, and then the prediction came back to be displayed in the UI. Now, although the predictions are fast, the network latency adds enough delay that real-time predictions were not possible. But because BigML's decision trees are extractable and require very little resources to create predictions, your browser can actually download the model from BigML and then use JavaScript locally to generate predictions in real time. So this feature is currently available for models, ensembles, and clusters. And even better, we'll be open sourcing the JavaScript libraries that make this possible. So if we just come back to one of the models we just did, we can actually see this in action. If we go to the prediction tab, for example, we can see that the prediction is already filled out for this form value. And as I move these sliders, it'll actually change in real time. You can see the confidence change there. So let's do, how can we make this guy look better? Less than 0, no, duration. Oh yes, longer duration is good. Oh well. Anyways, you can see that the confidence is changing there. Maybe a new car. All right, greater than 7 years. Anyways, as you move these sliders, this prediction at the top is changing in real time. And also notice that we mentioned before the missing strategy. That selection is right here. So by default, if the tree reaches a point where it doesn't have a value for the split it needs to decide, it'll just stop there. Or you can change this to proportional, and it will continue past the unknown value and then combine the results from the sub-branches. All right, so the next feature is that I'm quite happy to introduce is fast ensembles. Although, since we keep improving the ensemble speed, I prefer to call this faster ensembles. But this latest improvement is a natural extension of our in-memory modeling algorithm that we introduced earlier this year. So we still have a streaming algorithm for extremely large data sets, but if we can fit them in memory, then the model speed is 10 times faster. So to understand this latest improvement to the ensembles, let's define a few terms. First, for an ensemble with n models, we have 4 stages that consume time. The first, which we'll call F, is the time it takes to fetch the data set from our storage. Next, we have our modeling algorithm requires the data set to be in a special form before analyzing. So we have to perform a transformation step, which takes t seconds. Then there's the actual modeling process, which requires m seconds. And finally, it takes s seconds to store the completed model. Now comes the interesting part. If we look at how long each of these steps takes, we discover something. For a large class of data sets, especially the ones that fit in memory, the transformation time is typically much longer than the modeling time. Moreover, since the model is essentially a summary, compressed view of the data set, it's much smaller than the data set, and the storage time is quite a bit lower than the fetch time as well. So the insight we have is that if the data set can fit in memory, then we can perform the fetch and transform steps at once, and then build several models rapidly in memory. In the extreme case of using one node, we can see how much time, or we can estimate how much time this can save. Essentially, we save n-1 iterations of the worst 2 components, the fetch plus the transform time. Now, there's nothing to configure for fast ensembles. It's a passive feature that is always running and making things faster. All right, so the most significant feature in our late summer 2014 release is the availability of Anomaly Detection, our second unsupervised learning offering. So to get a better sense of how Anomaly Detection complements BigML's existing algorithms, let's take a look at a summary of BigML's current learning abilities. So first we have our decision tree algorithm, which is an example of supervised learning and requires labeled data. So recall that labeled data means that each row of data consists of input values and a known output value, often called the label or objective. The machine learning task then is to build a model which can predict this label given new unlabeled inputs. The decision tree is essentially a function which maps the inputs to the label. Next, we have clustering, which is an example of unsupervised learning. Whoop, going too fast. And does not require a labeled data set. The goal here is to discover structure in the data itself, specifically to group the data by similarity. And now we have anomaly detection, which is also an example of unsupervised learning. Unlike clustering, though, like clustering, the goal is to store structure in the data itself. Except now we're interested in the task of finding data that is unusual. So for a more concrete example, let's once again consider the classic Fisher iris dataset. The first 4 columns shown here in green are length and width measurements of sepals and petals of 3 different species of irises. And the 5th column is the label consisting of the name of the iris species. So in the case of supervised learning, the task is to build a model that can predict the species of iris based on the 4 physical measurements. So the important characteristic again here is that the data to be modeled must contain a known value you wish to predict. So for the unsupervised cases, just imagine that this iris dataset didn't have the label, the species label, and it was instead just a list of measurements. For clustering, the learning task would be to group the data into clusters of similar measurements. In essence, we're trying to discover the labels. Although we won't know what the species names are, the clustering algorithm might be able to group the species together. For anomaly detection, the learning task would be to discover instances that seem unusual. For example, if the majority of irises with a long petal also have a wide petal, if there was only one that had a long, narrow petal, we would expect the anomaly detector to discover that outlier. So the goal of anomaly detection then is to find instances in the data that are most unlike all the others. So how does BigML find these anomalies? We have implemented an algorithm known as an isolation forest. Here's a high-level explanation of how it works. First, we grow a random decision tree until each instance is in its own leaf. That is, we force the model to keep splitting until it has isolated all the data into separate nodes. Now, consider an instance at the bottom of the tree. These are instances for which the tree required a lot of splits to isolate them. Essentially, these are the points that are hard to tell apart. Conversely, the points near the top of the tree require very few splits, meaning it was comparatively easy to separate them. From this, we can introduce a metric that measures the depth of each instance in the tree. And now we repeat this process, say 128 times. The instances will likely have a different depth in each tree, so we average those measurements together. The points that are consistently easy to isolate are probably anomalous. We represent this by transforming the average depth into a number between 0, meaning similar, and 1, meaning anomalous. The BigML workflow for anomalies is very similar to the workflow for clusters. For clusters, we provide the 3 API endpoints: the cluster endpoint for creating a cluster from a data set, the centroid endpoint for taking a cluster and a single instance and returning a prediction of the group the instance belongs to, and a batch centroid endpoint which performs the centroid computation over an input data set. Similarly, for the anomaly detector, we have the anomaly endpoint for creating an anomaly detector from a data set, the anomaly score endpoint for computing the anomaly score in the range 0 to 1 for a single instance, and the batch anomaly score for computing the anomaly score over an input data set. So what kinds of problems is clustering useful for? The first use is simply to enumerate the instances in a dataset which are unusual. This can sometimes be interesting all by itself. The idea with intrusion detection is to look at access patterns and automatically discover unusual patterns. So, you could be looking at network packet flags, analyzing kernel calls, looking at requests for elevated privileges, etc. For fraud detection, the idea is to look for invalid transactions that stand out. And we've actually been using this for several customers during development of this service. Another use case is to look at data that has been manually inputted and identify instances which might contain typos based on their impossibility. Anomaly detection can also be used to remove outliers. This can often improve the performance of the model process on a data set. And this is because if you think about the decision tree, the modeling process, the whole goal is to generalize. And the outliers, sort of restrict the ability for you to generalize very well. You can imagine you've got a corner of the space where you generalize well, but there's this one outlier that's pulling the values down. If you can get rid of those, then you can generalize better. And finally, an anomaly detector can be used alongside a model to assign what you might call a competence score. So this can be important if your input data is drifting over time from the distribution of the data that you use to train the model. So by comparing new instances to the training data with an anomaly detector, you can get a feeling for how competent the model will be at making a prediction with that data. All right, so let's go ahead and demo this. And I'm actually going to use a well-known data set, which is this diabetes data set from Pima Indians. And we'll take a quick peek in case you're not familiar. Basically what we have is a series of diagnostic measurements, plasma glucose, blood pressure, etc., and then a final determination or label of whether or not that patient has diabetes, true or false. And the original goal of this data set is to, of course, build a classifier that attempts to predict diabetes based on these input features. So let's go ahead and run the one-click data set. And again, remember the anomaly anomaly scores are done just directly from a data set. So this, under the menu here, you can see the new feature, one-click anomaly. You might expect to find it under the gear icons. You can see configure model, ensemble, and cluster. It will be there. It's just not there quite yet. That it is completely possible to control the parameters of the anomaly detector through the API. That already exists, but the UI hasn't quite caught up. Soon. All right, so let's go ahead and let the one-click anomaly run. And I can explain a little bit about the interface. So what's happening now is we're running over the data set. We're building all those individual trees to build out the isolation forest. And then what we're going to do is return the top 10 anomalous points. All right, so on the left-hand side, we have that top 10. 1 through 10, and if I hover over one of these, you can see now it's selected. And what we're seeing on the right-hand side in this data inspector is giving us information about that might help us, at least anyways, determine why that point was labeled as anomalous. Underneath, so the score is right here. We're representing it as a percent, so this is the scale 0 to 1 is a 0.6421 anomaly score. And we can also see a distribution of how each one of the features, how important they were in contributing to that instance being anomalous. So what this is telling us is that the diabetes pedigree, the insulin, and the plasma glucose were the sort of top 3 fields for this particular point of determining that it was anomalous. And so now we can actually look at the values, so we can see these are ranked. Diabetes pedigree was the top. We can actually see a distribution over all the instances of what that value looks like. This is the actual value of that instance, 2.3. And if we go way over to the side here, we can see that's at the extreme end of the diabetes pedigree. Likewise, if we look at insulin, this is also at the extreme end. And then the plasma glucose is also fairly extreme. And one might, not be surprised that having a high likely or high occurrence of diabetes in your family, having very high insulin and having very high plasma glucose would, be an indicator for diabetes, and yet here we have, for this particular instance, that diabetes is false. And so that data point is really standing out as an anomaly. And in fact, could actually even be an example of this could be labeled wrong. This might be, if you were really working with this data set, that's unusual enough because all those values are so extreme that it might be worth reviewing that file or wherever you got this data from and seeing if there might be an error. Okay, we can also look at the second data point here. And this one, of course, has a slightly different field importance anyways. It has diabetes pedigree, and then this diabetes flag, tricep skin thickness, etc. So let's see how these values are varying. So diabetes pedigree, that's at the extreme end again. The second one is diabetes is true. Well, that's also the smaller class, but skip over that for a second. The tricep thickness at 63, also at the extreme end. So I would take away from this that this data point is probably really just an outlier. It's at the extreme end of all of these distributions, and it probably is just an outlier. All right, so what else can you do with this anomaly detector? Of course, there's quite a bit more. We could score new points in the same way that you can make a prediction with a model. We could come in and add score a new point. So we could create a new input value and ask it for an anomaly score. So for this particular input set, we have an anomaly score of 63%. If we come back and look at anomalies, we can do a couple more things with this. You may have noticed there's this select option, and there's stuff grayed out down here. If we wanted to see these 10 anomalies, if we wanted to play with them directly, we could actually just click select all there. And if we create this data set, what we're going to get now is a new data set that just has those 10 instances in it. Of course, through the API, you can control this count. But now we can actually see a histogram of these. This is a data set of just those the points that were labeled as anomalous. We can also do the corollary to that. We can select, for example, if we wanted to take out these two that we think are suspicious. Maybe we just want to get rid of those data points before we model. We can actually select those two, and this little toggle here. Now, when I create the data set, I'm going to get all of the data points except those two. And so now you can see we have a count 766, and that should be 2 less than our original data set, 768. And so that gives us a way to filter out anomalous data points. Now you might say, well, what if I want to do something more sophisticated? I want to take out the top 10 anomalous points and the top 10 least anomalous points, or something like that. Well, that's also quite easy to do. We can go back into our anomaly detector, and we can run a batch anomaly score. So remember, this is the same as doing a batch centroid or a batch prediction. It allows us to create the anomaly score over an entire input data set, and we'll just run it over the original data set. And we can configure how we want this output to look. So I'm going to go ahead and put the header row back in. And we'll let this run. And then just like the batch predictions, I forgot to click the button, but just like the batch predictions and the batch centroids, what we get now is a link where we can download this as a CSV. But we can actually do one better than that. If we come back to our anomaly and anomaly detector and run the batch anomaly score, I'll do this again. Right next to these buttons, there's this new little button right here, this toggle. This allows you to also create a data set from the output. So if you've been watching our webinar series, I did, I think probably in the API webinar maybe 6 months ago, we did an example of a boosting algorithm, which we call Toy Boost. It was just for demonstrating. And part of that algorithm, we did a batch prediction to get the weights, and then we downloaded the CSV, and then we re-uploaded the CSV to create a new data set, so that we could do the boosting by recomputing the weights. This new feature will allow you to take the output of the batch functions and directly create a data set. So you can actually redo that Toy Boost all in the cloud now. But let's go ahead and let this run, and I'll show you. All right, so this is similar to the output we had before, except we only had the option to download the batch anomaly score as a CSV, whereas now we have this additional link to output the batch anomaly score as a dataset. Let's go ahead and click on that. And here we see we have the contents of the original dataset plus
an additional field called the score. So each point in the original dataset now has an anomaly score added onto it as an additional feature. And so if we wanted to, we could actually now do more advanced filtering using our filter dataset feature. And we could, for example, filter on the score. And we could choose only points that have a score between 0 and 0.55, for example. And now we've created a data set where we've removed all the points that had an anomaly score of 0.55 or higher. So this would give you the ability to control exactly how you want to filter your data set to remove either anomalous points or perhaps even to remove normal points if you want to create a data set with only the most anomalous points so that you could analyze those further. You could do that as well, of course.
So, as with our other machine learning services, BigML's anomaly detector is so easy to use that it's easy to forget the complexity that is being hidden. Quickly handling high dimensions, seamless handling of mixed data types, and being able to interact with a scalable cloud algorithm programmatically through BigML's API are all made easy. Now, there are a few things that didn't quite make it into the release that I actually did right before this webinar. But they are coming real soon, and I wanted to cover a few of those. So as I mentioned earlier, we'll be adding a configuration panel for the anomaly detector, although as I mentioned, all of the parameters that are possible to configure, you can configure through the API. And we'll also be bringing text analysis to the anomaly detector. It's not quite there yet. So project management, this is a feature that's been requested by a lot of customers and which we are excited to be finally bringing to the interface. So this will make it easier to group related objects in BigML together. Now the next two items, the in-memory sample server and the dynamic scatter plots, these evolved out of a need to visualize the output of the anomaly detector. And we're actually going to we've generalized them so that they'll be applicable to just data sets in general. It's a very powerful tool that we're excited enough about it that we're going to take a walk on the wild side and demo a pre-production version. So this is sort of what it will look like in production. It's at least a sample. So this particular data set is for a analysis of concrete. So it's what went into the mix, what was its tensile strength, all this kind of variables. And what we're looking at here right now is on the x coordinate, we have the cement feature, and on the y coordinate, we have the score, and it's also colored by the score. And this is a multi-dimensional data set, obviously, and we can actually change the axes and compare any two features from the original data set together. So we could, for example, we could set super plasticizer here, and we could set, that's a good one for the score. That was that score, that's fine. Maybe blast furnace slag. Ooh, not that one. Course aggregate. Anyways, this gives you a feel. This interface is fully interactable, or you can interact with it. Obviously, if you hover over here, you get the data inspector on the side here. This allows you to see all the values for that specific point. You can also click and drag. Well, maybe you can't in this one. You'll be able to click and drag to zoom. For the anomaly detector, what this will allow you to do is to plot two coordinates and score the coloring will be the anomaly score, right? So you'll be able to look at, for example, the top two features over the entire data set that contribute to the measurement or determination of being anomalous, and the coloring will be, again, the anomaly score. So that gives you a nice visual way to explore the data set and see if there are any patterns or trends in your data that are contributing to the anomalousness. All right, so I'm actually, let me see. So I'm going to turn this over to Andrew to make one additional announcement, and then we should have time left for questions. So, of course, please don't hesitate to ask questions through email or in our online campfire as well. We monitor them 24/7 and are always happy to help out.